Chapter 5 introduces us into the idea of light and the physics of light. Now, why is this important? Well, because that's really all that we really have good access to. Through a telescope, you're seeing the light of planets. You're seeing the light of the sun. You're seeing the light of the stars. So that's what you're measuring. It's enormously difficult to send a spacecraft to another world to study it in person. It's so difficult that we've really had very few that have done that. We've had missions that have gone to the moon and back and brought back samples. We've had several unmanned missions to the moon. Many orbited the moon, a few landed on the moon. Mars, there have been several orbiting missions and some landing missions. Likewise with Venus, some orbiting missions and a few landing missions, but far fewer than for Mars. And then we've also had a couple of spacecraft, and only a couple that have gone to Mercury, and just a handful that have been to Jupiter, and really only about 4 that have been to Saturn, and only 1 that has ever been to Uranus, only 1 to Neptune, only 1 to Pluto. And all those, all the ones to Saturn, Uranus, Neptune, and Pluto didn't even stop. Well, the ones to Saturn actually went into orbit around it, but the rest of them didn't stop, and they just kept flying by. So they were only there for a short period of time as they were flying by, taking pictures and making measurements. So many of these things we have to study just by looking at the light. Now, light is an interesting sort of thing. If you understand the physics of light, then you can understand how the light was made. Well, if you study the kind of light that you get, you can figure out how it was made, and therefore you can understand what was going on, where it was made. First of all, Isaac Newton studied light. He wasn't the first one to do this, but he did study light, and he noticed something interesting, that if you have a light and you narrow it down to a little slit of light, that little slit of light, when it hits a prism, breaks out into a range of colors. And it's always the same range of colors. It's red, and then orange, and then yellow, and then green, and then blue, and then sort of a purple color. Technically, it's violet. Okay, now, Isaac Newton actually went ahead and stuck another color in here, which he calls indigo, which is sort of between the blue and the violet. And so it's kind of one of these hard to define colors, because different people sort of define that color slightly differently. Modern indigo is not exactly the way that he defined it, but still, I don't think of it as purple, but a lot of books put violet in there because Newton did. Now, Newton actually thought that this should be 7 numbers, because in his studies at the time, they were thinking that 7 was a complete number, and so was better than 6. And so so he put indigo in there. And for students, this actually makes it easy, because it's like a guy's name, Roy G. Biv, as a way of remembering the order of the colors. Red is always the least bent going through the prism. Violet is always the most bent going through the prism. So it's always the same range of colors in there. Newton then kind of wondered about, the possibility that each of those colors might actually be colors in their own right. And so he would separate out one of the colors to put through a prism to see if it breaks out into a whole bunch more colors, but it did not. Okay, that one color was pure. In fact, what you could do is take all these different colors and put them together to make white light. And that's actually a demo that I often do in class when we're on campus. Is I take spotlights that are several different colors, and I put them together, and when you mix them all together, they become white light. Well, Newton was not really the first one to try to start measuring light. He was measuring the properties of light, but Galileo actually tried to measure light too. He's famous for doing the telescope, but he did a lot of other things too. And he tried to figure out how fast does light travel. And so what he did was he stood on top of a hill, and then had a friend of his stand on another hill. and they both had lanterns at night, and he would pull the cover off of his lantern. The light would shine over here. The other guy would see the light, pull the cover off of his lantern, the light would come back, and Galileo over here would be sitting here timing how long it took. He'd be taking his pulse and count how many heartbeats it took for light to get from his hill to the other hill and back. What he found was it was like just a heartbeat. And so he had his friend stand further away, and it was still just a heartbeat. And then tried to get his friend to stand on a hill as far away they could see the lanterns, just a heartbeat. And so to Galileo's reasoning, that meant the light traveled instantaneously, because what was happening was that his friend's reaction time was actually slower than the time it took the light to travel. And so that to Galileo meant light was instantaneous. And it certainly is pretty fast. Really, it was measured for the first time in any sort of degree of accuracy by Ole Reaumur. Now, Reaumur was an astronomer that was looking at making ephemerises. An ephemeris is a table of astronomical events. And one of the things he was trying to do was make a table of Jupiter's moons. And so Jupiter's moons, they orbit around Jupiter, and they sometimes pass into the shadow behind Jupiter, and they sometimes pass in front of Jupiter. The idea of passing into the shadow behind Jupiter turned out to be a very important thing as a timekeeping thing, because the moons move around in very regular patterns. And so the idea would be, if you have a navigator and they needed to know exactly what time it is, clocks weren't very accurate on ships. And so what he would do is, the idea would be they'd make this ephemeris as to when these events were going to happen, and navigators would have a little telescope, and often the ship would put to an island and set up a little telescope and record exactly when these events happened and set the clock. Well, what Reaumur discovered was that if Earth and the Sun, or rather, if Earth and Jupiter are on the same side of the Sun, then that means that the events happen at one time, but if Earth was farther away, the events happen later than they were supposed to happen. And so Reaumur thought about this and realized that's because light had to travel an extra distance right there. And so you could figure out how far extra light had to travel and how long it took to do that. Now, at the time, they didn't know exactly how far everything was from each other, but they did know that Jupiter was 5.2 AU from the Sun. They knew the Earth was 1 AU. So they could start, drawing these orbits and figure out, well, if that's 1 AU between there and there, how far is it extra? And so they realized that light travels 1 AU in about 8 minutes, which means when you look at the Sun, you're seeing the Sun 8 minutes ago. And so this was one of the very first measurements here of the speed of light. So later, when they figured out how big an AU was, they were able to figure out that the speed of light is about 3 times 10 to the 8th meters per second. That's 300,000 kilometers per second. That is 186,000 miles every second. So that is the speed at which light travels. And so that's really fast, 186,000 miles every second. That's why Galileo couldn't measure it by measuring heartbeats. And so in equations, what you'd do is you'd use 3 times 10 to the 8th, or you use scientific notation, the calculator, for meters per second, or if you wanted to do kilometers, it'd be 300,000 kilometers per second.